All right. Today we have Dylan Patel. He is the Chief Analyst at SemiAnalysis, which is a boutique semiconductor research and consulting company specializing in the semiconductor supply chain, from chemical inputs to fabs to design, IP, and strategy. So today we'll talk about, I guess, specialized hardware for AI in mainly, but we'll also talk about the broad trends in semiconductors. So, Dylan, welcome to the Data Exchange podcast.
It's good. Thank you for having me, Ben. I'm excited to be on.
All right. So, you wrote this really interesting post on how NVIDIA's CUDA monopoly in machine learning is breaking. So, we'll talk about that. And PyTorch is a key actor in this post. So before we talk about some of the things in the post, so a bit of a baseline setting here. So PyTorch has long dominated the research community. I mean, for years now. In fact, I pulled data years ago, Dylan, that the PyTorch people cited around the archive posts and PyTorch versus TensorFlow. This was early in the PyTorch, just after PyTorch was released, maybe a year into it. And yeah, it was very clear that PyTorch had usability advantages from the outset. So clearly, research community, they dominate. But one of the things, Dylan, that I've yet to see is clear indication that they've surpassed TensorFlow in companies. And I only have one metric here, which is job postings. So for job postings, it seems like TensorFlow always seems to have more job posts that have the word TensorFlow compared to PyTorch. And there's many reasons for this, right? So, but is this also your sense that research is one thing, companies and enterprise is another?
I absolutely agree in some senses, but not all, right? So, to me, right, being from the semiconductor focus, I focus on where the compute budget is going as well, right? So, yes, TensorFlow has, significantly more usage in, CNNs and other more smaller models that tend to not have huge compute budgets that can be, you can do the inference on an edge CPU, or you can do it on the CPU you already have, right? Or simple devices that you already have, your IP cameras or what have you, right? It's not very specialized in terms of the hardware makeup that you need, or the compute budget you're spending, because the compute budgets are ballooning. But when you start talking about transformers, whether it's large vision transformers or large language models, especially, and as we go towards multimodal transformers, the compute budget is overwhelmingly there. And yes, the personnel count is not. The spend for a transformer is relatively higher on compute relative to personnel, just because of how intensive it is. These large models are. And so, my angle with this is focused more on the semiconductor side, of course. And to that end, right? Yes, CNNs are awesome, and they're going to change how a lot of industries work, and many other vision models and more smaller models. But the focus of the hardware, at least, is especially so on the large language models, and transformers in general.
So there's still a few areas where maybe TensorFlow has better tooling, as you alluded to, like edge computing, maybe support,
deployment in general.
Deployment in general, and then maybe support for many more languages.
Yep, I agree. I mean, like it's like if you talk to folks at Google, right? If you look at research papers from Google, the big exciting ones, Palm, Chinchilla, Switch Transformer, so on and so forth, right? These guys are all trained on JAX, right? They use JAX. They don't use TensorFlow, right? Which is like, which one is the important one? Is it the image model, or is it the one that all the research is being published on and is actually going to be the next wave of implemented models? And so that's the question to always ask. And yeah, definitely CNNs will always have their place, and TensorFlow will always have a place at the table. Same with Keras and so many other. But when you talk about this next wave, that if you look at the general media, what everyone's excited about, those models are PyTorch or JAX. They're nothing else, right? So it's always hard to boil down given how broad this industry is.
Yeah, and I think actually I talked to both the leads of TensorFlow and PyTorch both around the time when they were released, and I immediately switched everything to PyTorch. Of course, I didn't tell the TensorFlow people this, but I think people also forget, Dylan, that there were a lot of Torch fans. I mean, even DeepMind used Torch back in the day. So Torch, as soon as PyTorch became available, it kind of people checked it out right away. And the fact that it was easier to use, I mean, they did a lot of things early on that really propelled them to where they are now. All right. So now, I think in terms of the longer arc of history, your post is probably going to be correct. In terms of you know, there's going to be a lot of other successful accelerators besides NVIDIA GPUs and TPUs, right? So you know, so the timing, I hope you're right.
I mean, you know, just because the software's portable doesn't mean somebody beats NVIDIA at training hardware, right? Besides Google.
I mean, but I think clearly all you have to do is read around Hacker News or Reddit, and there's tremendous hunger for alternatives, right? You know, mainly around pricing, but for whatever reason, people want more alternatives. All right, so baseline for people that don't follow the space, Dylan. So I like your post because you lay out a lot of great stats. So the first thing that I think people don't realize is that while flops are increasing, flops is only one component of all of these things, right? So there's memory and memory bandwidth. So walk us through the kind of the trends in all of these flops and memory bandwidth.
Sure. So, I mean, if we look at just NVIDIA's hardware, right, over since you know 2016 to 2023 now, right, where they've had, you know, now they've had 4 generations, right, P100, V100, A100, H100 now. You know, the flops have increased, you know, significantly, right, more than the bandwidth. The bandwidth has not even gone up 1 order of magnitude, right, whereas flops have gone up 2 orders of magnitude. So less than 1 order of magnitude versus 2 orders of magnitude increase.
For the non-experts, explain why this is important.
Right. So flops are going to be your floating point operations, right? Think your matrix multiply, think your addition, think anything, right? I mean, it will, you know, any operation it is. And then memory bandwidth is, you know, your input and output out of the chip. Right. And regardless of what you're doing, you have memory, and that memory has to come from, you know, your data has to reside somewhere. And some of it will reside on chip, but a lot of it will reside in the main pool of memory. That main pool of memory is generally called DRAM. And that bandwidth is what I'm specifically referring to here, right? So how many floating point operations can a chip do versus how much bandwidth, how much IO, how many bits can it move in and out of the chip? And the disparity between the two has grown rapidly.
And also you point out even memory capacity hasn't kept up, right?
Yeah. So that's the other angle, right? Is so with memory, right? We've sort of hit a brick wall. Since 2009 or 2012, depending on who you ask, memory has flatlined on cost. You know, we would have order of magnitude improvements, literally in line with Moore's law, right? You know, from the 70s all the way till 2010, right? More or less. We had order of magnitude improvements every few years, or every handful of years. And it went from hundreds of thousands or even hundreds of millions of dollars per gigabyte of memory. Obviously, nobody had a gigabyte of memory in the 70s, but, you know, of DRAM, all the way down to, you know, we got to the single digit range in, you know, 2009 or 2012 time period. And it has stayed in the single digit dollars per gigabyte of DRAM since then. And that's bulk DRAM. And then obviously AI accelerators, they might use bulk DRAM, but in most cases, they actually use a more expensive form of DRAM, which, you know, provides higher bandwidth. But, you know, as you look at how NVIDIA, since 2000, right, you know, same comparison point, right, 2016, where NVIDIA had the P100 GPU, they had, I think, was it 16 or 32 gigs of memory. And now with the H100, they have 96 or 80 gigabytes of memory, but the cost per gigabyte is the same. So, that pricing has literally 4x'd on the memory cost. And now today, if you look at it, the cost of memory is 30 to 50% of the GPU cost, right? And then obviously NVIDIA does a 4x markup on what it costs to make versus what they sell it for. Ignoring software development and all that. So they 4x the cost of what it is basically in general. That's their simple pricing model almost for these data center chips.
And Dylan, memory is important because the models obviously are getting humongous, right? So even the largest Cerebrus chip, I think, as you point out, only has how much memory?
Yeah, so largest Cerebrus chip has I think it's off the top of my head
in the order of 50 gigs maybe, right?
Yeah, 40 gigs of SRAM, right? So 40 gigabytes cannot hold a 100 billion parameter model. The simplest way to do it is just divide by 2, 100 billion divided by 2. That's how much memory you need. But really, then you have to hold all the intermediate operations as well, and data streaming in and out like it. So it's really a lot more than 40 gigs that you need for a 100 billion parameter model.
And this is why Ion Stoica, my friend Ion Stoica, who's the co-founder of both Databricks and Anyscale, has long pointed out that the future is distributed, right? So, because of memory. So for those of us who don't follow this industry closely, how come these trends bifurcated? Is there physics? Is there supply chain? Is there lack of raw materials? What's going on?
Yeah, so on the memory side, cost scaling really stopped due to physics, right? The simple way to think of DRAM is it's a capacitor and a transistor, and that capacitor has had real trouble shrinking. It's been a really tough materials and, just physics problem in general, right? Chemistry, physics, etc. The manufacturing side, that's why we've had very, very little improvement there. On the flop side, right? So that's memory, whereas the flop side is more dependent on a handful of things, right? One is architecture, which architecture has improved greatly since 2016, since 2010, since even in the last few years, architecture at NVIDIA has improved.
NVIDIA has pushed a lot of things into silicon, right?
Right, exactly. So there's innovations there. There's a smarter way to move memory around the chip and some better ways to compute, moving to lower precision. Moving from 32 bit.
Yeah. And by the way, Dylan, one of the things that you, at least I personally, always kind of keep expecting is at some point maybe NVIDIA's ability to innovate and push things into silicon will enable some of these other accelerators to really, really leapfrog them. But that hasn't happened, right?
Well, so if anything, the pace of innovation is sped up, and I'll get to that. But architecture is one thing. On the other side is process technology. On the digital logic side has improved a lot, and while it didn't keep pace with Moore's law in terms of cost, you did get these density shrinks that DRAM didn't, right? DRAM was purely an economic industry, or still is, whereas logic, people are willing to pay more for density, even if that doesn't mean your cost per transistor goes down. And so, with NVIDIA, right, the question is, hey, is the architecture going to stabilize, or, is everything just going to be a dense matrix multiply, transformer? Well, no, there's still innovations constantly. And then on the architecture side, right, as you mentioned, distributed, that is NVIDIA's biggest advantage, because they acquired a company called Mellanox, Israeli company. And Mellanox was the leader in, NICs, networking integrated cards, right? So how do I communicate from server to server? So they were the leader in NICs, and NVIDIA's taken that technology and continued to develop it, and built their own networking solutions that no other company really has. So now it's not just, hey, what is my architecture? It's also, hey, what is my software and what is my networking? And how do I do distributed? Right? So now the interconnects is the biggest bottleneck, right? And so the problem set has moved from just one, hey, my chip is faster. Yeah, cool, you can make a faster chip, but no one cares about your chip being faster on this nano scale. I want to be able to scale it up to 1,000 or 4,000 or 10,000. For
a while now, it seems like this kind of a distinction between HPC and regular ML is kind of blurring a little bit in terms of the hardware and tools they use, right?
Yeah, it's well, the thing is, right, the HPC industry has been very slow growth. And AI is obviously explosive. Like AI far outpaces HPC now in terms of, whether it's investment or revenue for semiconductor companies and so on and so forth, even on the training side, right? No one sells $4 billion a quarter of training GPU of HPC GPUs, right? They sell $4 billion a quarter of HPC AI GPUs, right? So that's NVIDIA, right? Like, and there's all these other companies trying to compete with them, right? There's no market for HPC alone, and so a lot of the development is just getting piggybacked off, right? And NVIDIA to some extent has said, hey, we don't really care about floating point 64-bit formats, right? Like we'll support them, but we won't focus on it. And that left a room for other competitors like AMD to win these Department of Energy contracts,
Right.
also through cost and some other things that they've in CPU and some things that they have, but NVIDIA sort of said, we're going to focus only on ML. And if you want to use HPC, it's supported, but our focus is ML. And ML is the biggest high performance computing problem in the world, right? There's no other, problem that is this big.
So, so at a high level, in terms of, I guess, economic importance or economic share, what's the split between inference and training?
So that's a really difficult thing to quantify, right? Because if you were talking about purpose-built chips, then training far outweighs. I'd bet 90-10 or 80-20. NVIDIA's is something like 70-30. But then others.
No, but in terms of budget, right? So once you train the model, so you spend so much to train the model, then now you deploy it. Now you've got inference.
Yeah, again, it depends heavily, right? Like a CNN, right? For example, an image network that you're putting in, say cameras all around, the city or whatever it is for for facial recognition. That costs nothing to train.
What about
but your inference cost is huge.
What about Chat GPT, right? So you train it, and now you open it up to the world.
Well, the funny thing is that I'm pretty sure they're just using that so they can get all their fine tuning data and their multi-shot and all that. But anyways, on their inference cost, it's still one, they're doing it on A100 GPUs. They're doing eight A100 GPU nodes for inference as well. But
so how much of inference can you do on CPU?
So not large language models, you can do a ton. Large language models start to get a little bit more difficult, tricky, but Intel added a new accelerator for inference. It's basically a tensor core, if you want to think about it, right? It's a tensor core in every single CPU core for their new generation of CPU. So clearly they see the value in inference, acceleration being much, much faster as well. But yes, most inference today, I'd wager over 90% is done on CPUs. Because it's you have X% of your workload is inference, but then everything else is you're still doing that, right? You're implementing that as a part of your larger workload. So there's, if you have to throw the data over to an accelerator and then throw it back, that costs so much power in terms of data movement and cost in general, right? Like, so it doesn't make sense. So you still inference on a CPU in most cases.
So the trend line, this bifurcating trend line that we talked about between flops and memory bandwidth and memory, is that's going to continue?
Yes, flops will continue to grow faster than memory bandwidth, and really memory capacity and memory bandwidth. But the fun thing is that the chip-to-chip speeds are increasing, right? So again, distributed, as you mentioned earlier. That's the path to increase your memory bandwidth. Is actually I'm just connected to 10 different chips or 1,000 different chips, and so I have all this bandwidth available to me.
Right. So as I said, so the thesis of your post, the long arc of history, I think will be proved correct. I think a lot of people, I think, have kind of speculated that there will be other accelerators, right, besides NVIDIA and TPU. So I think basically what you're saying is the companies behind these accelerators don't really have the resources to build their own software stack like CUDA or XLA. And even if they do, this is a problem because you'd have fragmented software system. So the natural solution is kind of an open source software stack all the way to the accelerator instruction set. And what you're saying is maybe we're at the cusp of that happening. I think basically everything you said there might be more on the optimistic side. Am I?
Yeah. So I mean, the first thing is, right, like, hey, OpenAI Triton PyTorch 2.0. PyTorch 2.0 today only works on NVIDIA GPUs and CPUs, right? Like, of course, this is, but the point is,
but the
easier to implement.
The thesis is it will expand, right? So.
Right, and there's, I mean, even yesterday, AMD pushed, and then for OpenAI Triton, right, that's only NVIDIA GPUs, because OpenAI built it for NVIDIA GPUs, right? That's what they use. But of course, they made it more portable, and so we saw yesterday AMD upstreamed a huge chunk of Triton code for their GPUs, and I knew this was coming. I talked to the company before I published my article. Of course, I talked to all the accelerator, all the hardware companies. Tenstorrent is also trying to implement into Triton, although they're still further behind. But there's multiple companies that are implementing into either PyTorch 2.0 or PyTorch 2.0 into Triton. The entire vertical stack. So it's coming. It's just the main thing is, if you want to switch software stacks, your new software stack has to be better at what your old software stack did. Whereas all these AI hardware companies are saying, hey, this works better on our hardware. It's like, cool, but like, what about on NVIDIA's hardware? Right?
I think
it's like, oh, it doesn't support that.
So a bit of history for our listeners: when these generation of specialized AI accelerator chip startups launched, they all were trying to build their own software stack, right? And now it seems like what Dylan is saying is now they may not have to do that anymore.
Well, so there's still a ton of work they have to do, but it's in comparison to what they had to do before PyTorch 2.0 and Triton, is significantly less, right? It's
what
actually
happened to so basically the idea here is that OpenAI Triton, PyTorch 2.0, this or any combination of those two will get you as close to QBLAS as possible. QNN and QBLAS. I mean, you're not gonna sacrifice any performance, right?
In fact, when you use that, you get a performance increase. So I think the PyTorch Foundation tested the 7,000 most starred models on GitHub, and they got like a 30% increase. The exact numbers in the article, but yeah, they got a performance improvement by moving to the stack, which means everyone will move to the stack if you get a performance improvement. Not instead of the other way around, being like, hey, we have this new software stack, it's portable. Oh, but it's performs slower, so why would I ever use it? Because 90% of people are still going to use the GPUs they have today or the NVIDIA GPUs that they're planning to buy, right? It's very few people care about portability in reality.
So who has to invest to make this kind of timing faster in terms of the implementation? So who has to do the investing here? Is it the PyTorch community? Is it TensorFlow community? Is it name your favorite deep learning framework community?
Yes, I mean, the only way to beat NVIDIA is in software, if you really care about it and having portability and so on and so forth, is if you support everything, right? If you leave the bulk of the work up to the hardware company, whether it's a startup or it's AMD and Intel or whoever it is, they're not going to build something. I mean, even TPU support. It's harder to use a TPU than it is to use a GPU, right? And TPUs have tremendous work and effort behind them, and even Google has not built something as robust of a software stack for training a large language model. They just haven't, right?
So is it the hardware startups that will have to invest?
I mean, they have to invest, and they are, but they need help and heavy lifting from the users, right? And I would bet OpenAI and Meta are two of the top 5 users of NVIDIA GPUs in the world. I would bet they're even higher than that, but at least 2 of the top 5 of NVIDIA data center GPUs, and they're the ones that have to build it. If they care about portability, they have to force it down. Otherwise, NVIDIA is just going to continue to lock people in.
What about the cloud platforms? Obviously, Google has TPUs.
Yep. So Amazon, with their Trainium, it's not that good first generation, but future generations will presumably be better. Trainium is going to be support in PyTorch 2.0. So you have to support the open standard. Otherwise, it makes no sense to use it, right? Google, I guess, has enough inertia behind them that they can get away with it a bit. But even then, they have XLA on PyTorch, right? So that you can use TPUs through PyTorch. You have to solidify on an open framework that supports multiple hardware vendors, but that open framework also needs to be the best way to use it on the existing incumbent NVIDIA hardware. That's the only way you can beat the monopoly.
Oh, so you mean so whatever happened to OpenCL or whatever it's called now, One API?
So One API is developing along, and they're developing. So Intel sort of has the same idea, right? Hey, let's make sure this works really well on NVIDIA and our hardware, not just our hardware, because that's the only way you can get people to do it. But it doesn't work nearly as well on NVIDIA hardware. It's missing a lot of libraries. Plus, Intel hardware is nowhere to be found. They still haven't, they're supposedly shipping it to a Department of Energy supercomputer, but
Yeah,
that's about it.
they're supposed to have a GPU, right?
Yeah, they canceled their first one, GPU. Their second one got delayed. So it's like, you have to have the hardware available too, right? Like, and your software stack has to be better on NVIDIA, and neither of those exist today. So it's that's not the way.
So where are we as far as this open source software stack for the best known hardware startups, Cerebras, GraphCore, Samba Nova?
Yeah, so all of these folks are, looking, they have their own software stacks today, right? Triton and PyTorch 2.0, especially the deadly combo of PyTorch 2.0 feeding into Triton, is very, very new. In fact, it's not even mainlined yet, right? For PyTorch, it's still in the night lease phases. I think they released the full version in March. But these hardware startups need to pivot, right? So I know for a fact TensorFlow is pivoting. They have their software stack, but they're going to make it support this vertical stack completely in the future, right? And Cerebras needs to do the same thing. GraphCore needs to do the same thing. I've talked to all these companies, and they said they're coming up with their roadmap and adjusting it to, because this is a big change that happened more recently, right? PyTorch 2.0 was kind of well known, Triton was well known, but how good this combo was not really fully understood by the wider community up until I would really say NeurIPS and the PyTorch conference just a month ago. Or a month and a half ago. That was really when people realized, oh wow, this is a big deal. And now that AMD's got mainline support or adding support for Triton through PyTorch, it's just going to continue to accelerate. So everyone needs to they need to shift their roadmaps into supporting these two softwares. Otherwise, it's all for naught, right? Because the only hardware that works today is, again, NVIDIA GPUs on these two.
So Intel has One API. AMD has what it's called, ROCm.
Yeah, ROCm.
Yeah. So then what you're saying is they need to shift more of their focus towards this open source software stack.
Well, yeah, exactly. And their software stack will still be required, right? There's so much more software underneath these two base layers, right? Related to the hardware, and especially on the distributed side. But yes, you need to support these, and you need to make it your number one priority on your software teams to support Triton and PyTorch 2.0.
And is that it, or are we missing some companies in China, India, Israel?
Yeah, I mean, so there's tons of the European Processor Initiative is supposedly going to support the latest PyTorch. India, I'm not too aware of any training hardware startups. China, there's the whole sanctions dealio. So
which we'll get to.
Yeah, who knows? There's a lot to say there. But as far as like Cerebras, GraphCore, Samba Nova,
what about whatever happened to Habana inside Intel?
So they're still developing that. The software stack for Habana is more mature than the software stack for their GPU and One API. So Habana does not use One API, by the way. It uses its own separate software stack, which is confusing to say the least. And they need to support it as well.
So if we talk again in exactly 1 year, where will we be in terms of this open source software stack, you think?
I think a lot more companies will have supported it or announced their support coming soon. I think Nvidia will still have 99% of hardware sales, but
Oh,
it'll
1 year from now.
public hardware sales, right? So obviously, Google's going to use TPU, and Amazon will start using Trainium, and so on and so forth. But as far as public, people buying, chips, I think Nvidia will still remain like 99%. Maybe AMD will crack a little bit of that nut, but not too much of it. It's a slow grind, right? It's not like it happens overnight. But this is the beginnings of, an open software stack where other people's hardware is supported. And it's once other people's hardware is supported, once you can start renting for a couple dollars an hour any hardware you want in the cloud. Once you can buy this stuff for not too expensive and it supports this software stack, that's when you can start to think about, oh, okay, well, now what if Meta or Microsoft or whoever it is wants to order 10,000 of these, 100,000 of these, right? Then you can start to think about that.
Oh, 10,000
GPUs, right? Or accelerators,
GPUs
right?
from another vendor, and where they're very comfortable that all of their software will run, right?
Yeah. They're not going to take that risk just out of nowhere.
Exactly the same models that you don't have to rewrite, right? I mean, your PyTorch code will run as is. It's basically the vision.
Yep. And the beauty is PyTorch 2.0 does that and already, right? So it's just about a matter of getting built into PyTorch 2.0 rather than have it, which brings you to a much lower level than or higher level, depending on which way you think, than 1.0 did, and same with Triton. Much less work for the hardware to implement.
So will TensorFlow and JAX be MIA from this kind of shift?
I mean, I think JAX and TPUs will still be a huge segment, right? Especially within Google, and then some companies like Cohere, using it for large language models. But in general, I think TensorFlow doesn't seem to be, it doesn't seem like Google's even focused on large language models for TensorFlow. Right. So it'll always have its place with other kinds of models. But if you're a believer that large language models, transformers are the future, which many people in the community are, then I don't think TensorFlow or Keras are really viewed as the big thing. Now, JAX, yeah, definitely, and there is an argument that you should use, Google Cloud and TPUs. There is an argument there that's relevant.
But what about JAX hooking into this kind of new software goodness around Triton and all of these things?
I would be surprised if they hooked into Triton, because, I mean, it goes JAX to XLA, and while XLA theoretically supports a lot of hardware, right, in practice it kind of doesn't, right? Yeah.
So in many ways, kind of, what this is reminiscent of is when you talk about PyTorch Prime, it's basically like RISC for the PyTorch API.
If you're watching the video, I have a RISC-V shirt on right now, so perfect, right? No, I mean,
which allows me to segue to our next topic, which is RISC-V. Where are we? And by the way, for our listeners, maybe Dylan, give them a very high level overview of what RISC-V is and why is it significant, and then a status update.
Yes, I mean, CPU instruction set architecture has always been a hot, contentious debate, right? There's IBM's various instruction sets that still exist today, for a certain subset of set customers. There's the Intel AMD x86 sort of alliance. And IBM kind of forced that to them, right, back in the days. But anyways, there's x86, which is sort of the dominant CPUs from Intel and AMD. And then there's ARM, which, ARM licenses their cores, and many people are implementing their cores all the way from, NVIDIA's doing Grace Hopper, right? Grace for ML, all the way down to like Graviton at Amazon, and there's many more.
And Apple, right? Apple.
Yeah, Apple uses ARM. They'll use the instruction set. There have been other attempts at more open standards in the past. ARM used to be very open, but ever since sort of they started, the merger with NVIDIA, sort of acquisition by NVIDIA of ARM failed. ARM's kind of clammed up and realized they need to be profitable, so they've started, even suing their customers. They're suing Qualcomm, for example, which is one of the, the biggest chip company that doesn't manufacture their own chips in the world, right? So biggest chip company in the world, basically, one of them. They're suing Qualcomm. ARM's really closed up a lot over the last few years, and ARM was viewed as the open CPU instruction set, right? x86 was closed; you could only buy it from 2 companies, and ARM was, well, anyone. I could buy an Apple, or Apple phone with ARM, or I could buy Qualcomm, or I could buy Samsung, so on and so forth. Amazon, all these people were making ARM chips. Hundreds of companies make ARM chips today. But that's quickly transitioning to RISC-V. So RISC-V is, it was birthed out of Stanford, and it's a new reduced instruction set architecture.
And Berkeley, because Patterson.
Oh yeah, sorry, Berkeley. Yeah, I'm sorry. Yeah. Berkeley and Stanford, and it's generated a huge wave of innovation and changes, right? So one would think, oh, it's just an open source instruction set, right? You still have to build the CPU core, which is not trivial, right? The instruction set is like, it's like looking at a keyboard and saying, hey, I have a computer now. No, you don't have a computer, you just have the keyboard. Or looking at a dictionary and saying you can speak fluent English, right? Like, no, you just have a dictionary.
So it does. Where are we in terms of actual chips?
Yeah, so the amazing thing is, like, it's very quiet, but in fact, the smartphone you're looking at, if you have a Qualcomm-based smartphone, they actually use RISC-V for security. If you have, your Bluetooth is using an Andes chip, which is a Taiwanese company, and they're using RISC-V for a lot of the control and it's not exposed to you, but actually there have been billions of RISC-V cores shipped already. Right. So, but it's not in anything user exposed, really. Right. Like, you're not going to buy a laptop and say, oh, my laptop is the one that has the, my CPU on my laptop that I'm directly able to write code and execute it is using RISC-V. No, not yet. But my Bluetooth might be, or my Wi-Fi module might be, or.
So when will that happen on the laptop side?
Laptops, I think actually PC is the furthest away. I don't expect RISC-V to penetrate that market for a while. But in the smartphone and wearables and data center segment, it's being put in rapidly, right? The beauty of it is that RISC-V is just an instruction set. But if I want to make a chip for video encoding, right? Specifically designed for video encoding, I could implement the RISC-V instruction set, but then I could implement all these other instructions that are specialized, and there's no one telling me I can't do it. I'm allowed to do whatever I want.
So the main the value prop is completely open.
Yeah, the value prop is that it's open. There's no one controlling it, and there's a whole lot of innovation happening, right? Like, especially on how you design chips, right? The way you design chips, you wrote System Verilog 20 years ago, and you still write System Verilog today. Now, if you asked a software developer that same question, what did I do 20 years ago and what do I do today? You're going to say, heck no, I have way different tools. And of course, there are innovations in the design space, but there's so many RISC-V based companies that are actually, their claim to fame is not RISC-V, it's that they're designing chips in a completely different way, right? So some people might have heard of Sci-Fi. They're using a tool called Chisel, which is open source, and it lets you write, it lets you do your definition of the hardware at a much higher level. Right, which you can think of like, hey, that's going to speed up my pace of development, right? Like, nobody writes assembly today, right? Nobody, yes, people write C++, but a lot less than write Python or JavaScript, right? So it's like, it's the same attitude that hopefully comes to hardware. It's like, hey, like, why can't I just write in a higher level language? Why can't I have, a million people capable of creating hardware rather than 100,000?
What about RISC-V in the data center? Is that going to happen? ARM in the data center took a while, right?
It took a decade for ARM, right? Between when they announced they wanted to go to the data center and really high volume, right? I think they announced it in 2011. And we really only saw really big deployments from Amazon in 2021, right? Maybe 2020, right? Very big deployments. So RISC-V in the data center, is it going to take 10 years? I don't think so. I think it'll take less time. Because there's the one angle of hardware accelerators, right? Well, why would I implement my custom ISA for everything? Why don't I use RISC-V and then add my own custom instructions? And then from those custom instructions, I can have all the acceleration capabilities. But if I want to run Linux, well, then I don't need to do much work, right? Like, I just already have it there. Or like if I want to build a compiler, I can take the open compiler and I can modify it so it supports my new capabilities, right? It's much less work on the hardware side. And then the other side is like, hey, there's companies building CPU cores that are going to be high performance, right? ARM wise, nobody was building high performance, really like comparable to Intel and AMD for, in 2011 or in 2012 or to 14 or 15. It took a little bit of time before cores that were of that performance started coming.
And then
but on the RISC-V side, there are companies doing that today, and it'll trickle in over the next few years.
So the other thing about ARM from the get-go was kind of the halo around energy efficiency. So I'm assuming RISC-V checks that box as well.
Yeah. I mean, it's definitely an advantage that RISC-V that potentially they have is that energy efficiency advantage. I mean, it's just there's less baggage, right? And people argue about how much the baggage is. Some very great people will say it's 10%, and some other people will say it's much higher. So I stand more in the it's more like 10-20%. Not counting the software, but just like the hardware baggage. And then software is going to be additional baggage over that. But if you think about that, right, like regardless of what it is, it's a significant amount of energy when you start talking about hundreds of thousands or millions of chips deployed. And so yeah, RISC-V checks that box. It has the least baggage, right? Given it was designed the most recently, and it was, it's a consortium that decides everything. So, the biggest criticism is the consortium doesn't decide things soon enough, right? They're slow, which is fine. That's got advantages too, because they make sure they make the right decision.
Right. And my closing topic is geopolitics, which is kind of this, I guess, the attempt to kind of, how to put it diplomatically, isolate China from the most leading edge chips, right? So there's certain choke points in the semiconductor industry. So how do you think this is going to play out?
Yeah, so it's a big deal. I mean, the decoupling of the West and China has really started in 2018 when Huawei got sort of sanctions put on them, but it's really accelerated. And last year, in the latter half of the year, it jumped by the biggest amount. Right? China is not, cannot buy AI chips or build AI chips built at TSMC, which is the biggest foundry in the world. They can't do that unless at a certain performance level. If it hits a certain performance level, it's not allowed to be shipped by TSMC to China, and that puts a whole cap on things, right? And they're not allowed to buy.
They can't buy equipment from ASML.
Yep. Right? They can't buy equipment from.
Although ASML is complaining because their competitors can still sell equipment because they're not the.
I mean, for the most part, the equipment, the best equipment that ASML has, they can't sell. But then a couple steps down, they could, and so can their competitors in Japan, which are much smaller. But like for the most part, I think the sanctions are mostly fair in terms of what's blocked.
What about what about memory chips?
Yeah, so memory is not really. Well, so there's a few things, right? There's one is if you're a company in China building memory chips in China, you're restricted from equipment in a big way. But if you're selling memory chips to China, there's no problem at all. There were basically no sanctions put on that.
So how far back generation GPUs are Chinese companies still allowed to buy?
Well, so NVIDIA made a special version of their A100 GPU that can ship to China, and so that's pretty much it. But after that, it's going to be hard. They're not going to be able to buy H100, and it wouldn't make sense for NVIDIA to make a special version that gets below the requirements of the Department of Commerce and such on, right? So, and State Department and so on, right? So NVIDIA, China's sort of stuck on basically A100 level. It's called the A800, by the way, which is such a funny name.
But this also affects all of the bleeding edge AI startup chips, right?
Yep. I mean, some of them, their chips don't fall under the regulation threshold, but some of them don't, right? Like I can, Cerebras cannot ship a Cerebras chip there anymore. They just can't. That's like illegal. They're never going to be able to anymore, right? So it's just an example of a company we talked about earlier.
I was thinking as you were talking, well, maybe this will spur the Chinese community to really hop on Triton and
Which, I
and
mean,
PyTorch 2.0. But then if the hardware they're allowed to use is old, so does that really help? I guess it
well,
still does, right?
yeah, I mean, regardless, you need to extract more performance through software, and you need to build larger systems. If you can't get the new hardware, you just have to build larger systems and extract more through software, and that's absolutely what's going to happen. You know, it's you know, it'll definitely slow China,
So
especially as they
this
move forward.
includes so all of the leading edge AMD GPUs and potentially the new Intel GPUs are also covered.
Yeah, yeah, it's a certain level of bandwidth and a certain level of flops that the
I see.
government said if you achieve both of those, you can't ship. And so AMD's newest GPUs and Intel's, you know, upcoming and for data center, right, the AI ones, those are also blocked. Cerebras, like, you know, a lot of these companies have blocked chips. They're not allowed to ship.
And the reality is, for China to build their own chips, it will just take years and years, right? Because the equipment they don't have, maybe the talent they don't have. Um, yeah. And even if they are able to somehow get their hands on an ASML machine, it'll break down. They need maintenance. And then, of course, ASML keeps improving their EUVs, right?
Yep, yep. It's going to be really hard to replicate the equipment space. Software and AI and things like that. They're what you would call much easier to sort of innovate. I mean, it's not much easier to innovate, but it's a quicker developing field, right? Whereas equipment is such a, like, you know, I hate to say Scrum versus waterfall, but it's such a waterfall type development, and you can't really do anything else in that space, right? Like, so it's hard to like just completely flip it on its head and say, hey, we built a EUV tool today, because no, right? ASML, yes, they build EUV tools, but it's because Intel, TSMC, and Samsung gave them a crap load of money a decade ago, bought a big chunk of the company, and then every time ASML had a prototype, they shipped it to them, and then they said, hey, fix this, improve it in this way. And China doesn't have that, right? So how are they going to build an EUV tool?
Yeah,
You know,
and then they spent years refining, kind of assembling the best components, right? ASML.
Yeah, and they have a huge supply chain that's also going to be blocked, right? So it's not as simple as, you know, hey, they'll have a EUV tool today or tomorrow, right? It's a decade, right? A decade type problem, right? And by then, you know, we'll be on, like, we'll be on gate all around transistors and blah 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 blah, right? Like, you know, it's a big deal.
And so, the Europeans, are they on board with all of these?
To some extent, but no, to a big extent, right? Like the Dutch are negotiating very loudly in public, basically saying, yeah, we're not going to follow the U.S. sanctions, and then the U.S. is like, can argue like, well, ASML, you know, a huge chunk of their company actually sits in the U.S.
Yes, yeah, exactly.
They bought, you know, Cymer, which builds the light source.
Yep.
They do almost all of the software in the US, right? Like there's other levers to pull. So it's a big, you know, political battle, but, you know, we'll see what the bureaucrats decide.
Now, in terms of the software for designing chips, you know, Cadence and all of this, these are all in the US.
So yeah, Cadence and Synopsys are US companies, and then Siemens, they purchased Mentor Graphics. Mentor Graphics is sort of the third place. So Siemens owns them. Siemens is a European company, but most of the people are in the US. So yes, EDA, how you design a chip is a huge chunk of it is in the US. And that's another angle that hasn't been sanctioned super hard, but it could be.
Yeah. And with that, thank you, Dylan. This has been a great tour. And I think, as I said up front, I think history will prove you right in terms of long term. It's just a question of timing as to how soon this kind of transition to this open source software stack will happen. Yeah.
Absolutely. Thanks for having me. And yeah, I mean, the title is inflammatory, but that's what you have to do in this day and age. You know, the facts are there, and I think, you know, we'll see it over time develop, and excited to see that developments. Thanks, Ben.
Thank you.